Hello, my name is Landon Ross. Welcome to my Lab 6 magnetic molasses. Here's an overview. We're going to be doing an intro, then going over the experiment and procedure, coding section, some discussion questions, and then the conclusion. So to start, for our purpose, we have to collect observational data of a magnet falling through a conductive tube of aluminum foil. And we're going to model the magnet/tube interaction computationally, and we're going to compare our computation model predictions with their observed data. Four fundamental concepts that we are using in this lab are magnetic flux, Faraday's law, Ohm's law, and Biot-Savart law, all four of which can be seen on the screen right now. And just a quick introduction to our results. Our average drop time was 1.0 seconds, and our projected drop time through the computational model was 0.4 seconds. So, starting with our procedure, first thing we did was mark the North Pole on the bar magnet, and then we held the tube vertically and positioned the magnet just above the tube, and then positioning our phone in a manner so that we can see both the top and the bottom of the tube. We dropped the magnet and recorded, using timestamps on the video. So for all of our drops, we went through the video and marked a timestamp for when it was entering the tube and when it came out of the tube. And that's how we determined the time it took the magnet to get through the tube. In this lab, our system was the tube and the magnet, and the surroundings is basically everything else, your hands, the phone, anything that's not involved with the experiment. So some possible error in this experiment are really just all centered around the time of the drop. So if the magnet is not right above the drop area or the tube, if we're not holding the tube completely vertical, and if you're not dropping the magnet completely down, these could cause the magnet to drop in inconsistent manners. And then through our computational model, this is just the graph that we got, again leading to the result that the predicted was 0.4 seconds. All right, now let's get into our two checkpoint questions for this lab. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So if this were to happen, we would have a greater induced current, which would lead to a stronger magnetic field, which would then create a slower falling magnet, so our fall time would be larger. And then if we were to put holes or slots cut into the tube, how would this affect the ring currents in your model? This would, interrupt the induction, and then we would have a more normal. It would, it'd interrupt the magnetic field, and we would have a more normal fall of the magnet. So, in conclusion, the purpose of this lab was to collect observational data of a falling magnet through a conductive tube of aluminum foil. And my results were that we had approximately 1.0 seconds free fall timed in real life. And then our computational model was 0.4 seconds. And then the takeaway for me was I was surprised how slow the magnet fell in the tube. Thanks for listening.